Good morning, guys. Welcome to OSI's fourth webinar. I am Gustavo Gonzalez, engineer and technical sales manager. I have been with Odessa Separator for 7 years, and today with me is Luis Buenagas. He is the technical services leader. He has been with OSI for almost 5 years. We hope you and your family around the globe are safe and healthy and taking all the necessary precautions during this time of the pandemic. We know things are tough right now due to the pandemic and the economy, but let's be optimistic. I know things will get better soon. And hope you're taking this quarantine to get quality time, discover new talents, read a book, and invest your time and things that you can bring us some value after this is over. How you know, one of the most common tools used for sound control is the Downhole Desander. This is due to the simplicity and the lower cost. Therefore, we decided on this webinar to discuss how to improve the performance of the Downhole Desander. We're going to show some test results and some analysis. On the agenda, we have sound production causes, sound production consequences, sound control management method, how Downhole Desander works, operation efficiency, parameters, well optimized, and conclusions.
Thank you, Gustavo. Appreciate your introduction. Thank you guys again for coming today to our webinar. In this section, we are to introduce sound production causes. We are to focus on what are the main causes for your sound production. And we are going to try to identify how these causes are going to affect the performance of your wells. So, the sound starts in a well because the rock failed. And the rock can fail because two reasons. We can address natural factors and we can address induced factors. In the natural factors, we can talk about many parameters or many phenomena that naturally happen in downhole. But we are going to refer mainly to the consolidation degree. And the consolidation degree, it is actually how strongly each sand grains it is come together. So how strong is the rock? We can find some portions that are consolidated, which means they are strong, and it's difficult for those rocks to produce sand migration. On the other hand, we can find unconsolidated degree, which are formations, typically older formations or deeper formations, together with older deposits or sediments, are commonly consolidated. Unconsolidated rocks are typically reservoirs with shallow formations or maybe younger sediments. So that's maybe the relationship. When you found a reservoir unconsolidated, that means your sand production is really heavy. The amount of sand you will be produced, it is really high. So prior to the drilling, prior to the production of the well, you need to start designing your sand control. That's why it's so important that the reservoir engineer, the geologist, characterize your reservoir and identify if you are producing from a consolidated rock or maybe an unconsolidated rock. This is the first factor that produces the sand production. The other one is induced factor, which are the factors that remove the well. Typically, when you drill a well, you want to produce high amount of fluid because economic reasons, right? So as soon as you drill the well, you want to start high production, which means submit the reservoir to high drag forces because the fluid production, because the fluid velocity. So all those variables, the fact that you are removing pressure from the reservoir, then your fluid is flowing to the post media, and you are releasing the pressure or your formation is submitted to plastic deformation. Those variables are affecting your sand production, and those are promoting your problem. We can address also the critical drawdown. The critical drawdown is defined by the pressure, the minimal pressure after which the sand is going to be produced in your reservoir. To determine that, you can use different tests. You can use thick wall cylinder test. You can use simulation models. You can use software with simulation models. But the idea is try to identify this threshold. Of course, it is really difficult to say like, hey, I'm not going to overcome this threshold because at the end of the day, we drill a well because we want to produce it. We want to produce the liquid and because we want the oil, right? So necessarily, we are going to overcome this drawdown pressure. The problem here is identify how critical is going to be this overcome, how critical is going to be my production pressure, comparing this with the critical pressure. Another reason that can remove the sand production is the frac job. Since the 70s and mostly nowadays, mainly US is producing through the fracking, right? So the fracking commit or combine different phenomena that remove the sand production in your well. That's why in the Permian Basin, it's so common to have really challenging reservoir, and that's why it's very important to plan, to analyze, and to identify what are going to be the possible solutions. In other fields, maybe we can address the Middle East, South America. They have secondary recovery, and they use water flooding. The water flooding is one of the main causes of artificial factor to produce the sand because many reasons. One of the reasons could be the composition of the water. The incompatibility between the water and the rock can remove chemical reactions like the hydrolysis of the quartz. We can have carbonate reactions. Carbonate reaction is going to remove the cement that keep coalesced or bonded the sand grains. When we do this, that's going to remove sand production. Another factor is changes in the capillary pressure. When your water cut increase, your capillary pressure is going to reduce. This factor is going to make easier the movement of the water to the reservoir. When the water can move easier, that means it's going to move faster. When it moves faster, that means it can remove or make easier the fine migration. So that's why normally reservoir producing through water flooding are so critical to design an effective and a really accurate sand control in order to keep the well running and in order to optimize the field performance. Okay, let's move to the next one. And we're going to discuss a little bit about how are the reservoir right now developed worldwide. So conventional, or typically we have conventional and unconventional wells. Conventional wells typically are recognized as well are drilling conventional deposits. That means normal permeability or high permeability. And then the reservoir is surrounded by natural seal. Could be old, could be impervious rocks, etc. Another type of well is unconventional wells. This means are wells which are completed in low permeability reservoir or reservoir with high density or viscosity fluid. For instance, we can name Thai sand, coal bed methane, shale, etc. Right now, in the Permian Basin, we use a different terminology for unconventional wells. So unconventional wells are wells drilled in unconventional or conventional reservoir, but those wells are completed in horizontal trajectories and has completed with fracking. So we drill the well, vertical section, horizontal section, then we frack the well and we start production. This phenomenon or this method is one of the main reasons because we have to address sand problems before we complete the well. It is so critical, and I want to maybe highlight these facts because sometimes we have initial wells that are starting production, and then we saw how these wells have different interventions because downhole problems, because perforations plug, because maybe they are using a gravel pack or any different type of completions, and they are affecting the performance of the well. So it is so important to address this problem before we drill the well. Okay, let's move to the next one. Okay, this is the typical profile for a well production, for a sand production, right? So in a conventional well, the sand production is gonna start from the beginning of the production. So we drill the well, and then the formation is gonna have a plastic hole deformation, which means we are releasing pressure, and then that's gonna transport the solid. Then the hole is gonna stabilize, and we are gonna have a normal trend of sand production, pretty low. But at the end of the production, the pressure is going to decline because again we're reducing the power of the energy, or maybe better the energy of the reservoir. That means the rock is becoming weaker because the production activity we are implementing, and then right now we are having a high sand production. This is conventional wells. For unconventional wells, we have a different performance. So we have the typical plastic deformation. But remember, because we frack the well, right now we are having not only the plastic deformation, we are having additionally the flow back of fracked sand. You know, we have to use some propant, which are going to be the additives we put in the water just in order to be inside the fracture and keep the fracture going. So that's why normally at the beginning of those unconventional well completion, the sand production is higher than normal wells. Now, if we continue with this curve, we see that there are no hole stabilization. We, instead of that, see different frac heat. A frac heat basically is the interaction between two wells in the same path. We can call this neighbor's well. So I have one well here producing right now, then I'm drilling a new one here, right? So the drilling and the frac job I'm doing in this new well is going to affect and is going to create a communication. The communication could be two types. Pressure communication, which means just the pressure that I am using to frac the well, my new well, is affecting my production. Or we can have sand communication, which means the sand I'm using to frac this well is gonna reach my neighbor well, my first well, and it's gonna affect his production, right? So right now I'm producing this sand that I'm using from this well in this well. That's very common. We call this parent-child relationship. Parent is the first well I have, child is the second well I have, right? We can see this more closer in the next slide. This one. If you see right here, we can check how is the density of the well per square mile. We can go from typically no severe density of well, which means 4 wells per square mile, and that means each well is spaced between 1320 feet until 1000 feet. And then we can have high density wells, which are around 16 wells drilled in the same square mile, and each well is spaced 330 feet. So the wells are very close, and of course the interaction is really, really close. In these high density paths, I have to be more careful. I have to maybe try to shoot my parent well down while I'm doing the perforation or the drilling in my second well, my child well, just in order to prevent sand migration from one to another well. We can see how is this density next slide. If we can move, please, Gustavo. This is the Permian Basin. I like this picture. It is really, really realistic. And it shows how the density of the well is so high. And you can imagine, even if the directions of the trajectories of the well are different, the interactions is really inevitable. I mean, there is going to be interactions. There is going to be affectation from one to another. and we need to care about that. Okay, it is really, really important, and you need to be aware of this phenomenon. So not only the way how I drill each well is going to affect my sand production. As we talked initially, the natural factor like the consolidation degree and the pressure is going to affect how critical is going to be my sand production. So that's why I like this picture too, because it is an example of how critical could be my well if I'm drilling in the Wolfberry or maybe in Delaware Basin. So for example, Wolfberry and Wolfcamp are high sand production reservoir. So for sure, if I drill a well in the Wolfcamp, I have to wait for production, for sand production. So I have to implement sand production measures, right? But if I'm drilling a well, maybe in Howard County, in Klein, in that type of reservoir, the bottom hole pressure of that reservoir is pretty low. So I can complete my well with ESPs, normally ESPs, and then I can set up maybe a no very elaborated sand control tool. But still I need to be aware that it's going to be flow back because the next reason. Can we move please? I want to give you this example just for you to realize how severe or how critical is the sand production when you are fracking a well. So this is a real case, this is a real well. So if you see there is a vertical section and then we have the horizontal section. In horizontal section, we are going to frac the perforations, right? So in this specific well, we are going to frac 10,340 feet of lateral section. For this length, we have to use 1 million pounds of sand. So on average, we have to use 1 ton of sand per foot frac, right? So an important percentage of this sand is going to remain in the fracture inside the reservoir. It's going to keep the fracture. But what about the rest? How much sand I'm going to get back? How much sand we are going to get from the fracture? Well, there are different theories and different investigations. We actually choose the more severe, just in order to give you an example of how severe the sand production. This is what we want to show you. So from the total amount of sand you are injecting in your well, on average, you can expect to have a flow back of 30% of the sand injected. If we go specifically to the case of my well, we use 21 million pounds of sand, right? So we are going to have 6.3 million pounds of sand back, which means I have enough sand to fill 2,715 more joints. This is a total length of 85,165 feet of tubing. If we think about it for a moment, normally we use 10,000 of length, 10,000 feet of tubing in a well. So with the flow back of the well, we are going to have enough sand to fill the total amount of joints that we use in 10 wells. That's in 8 wells, sorry. So that's crazy the amount. And this is the typical production profile for an unconventional well. If you see, you're going to have an initial high production, which is a peak, which goes normally between 15,000 barrels to 5,000. So it's a huge range. Then we're going to have a declination, and then we're going to have an stabilization of the production. This is the normal production profile. We can call this well a parent well, which is the first well that I installed in a pad. Secondly, the next graphic on the right, you can see a parent well profile, which means the well affected by a child well. So remember, initially I have an initial well, and then I drill a new one here. So the frac job I do right here is going to affect my new well. So that's why you can see that the production starts, I have a peak, then it's going to start declining. But at the moment that I drill the new well and I frac the new well, you are going to have a new inclination, a new peak, a second peak, which is sometimes higher than the initial peak. That's another reason why you have to consider sand control measures before you drill these wells or before you complete these wells. You need to be aware about your drilling schedule. Problems. We can talk about many problems produced by sand production and different places where those problems are going to take place. We can talk about the reservoir problems, well problems, and surface problems. Going from bottom to top, problems on the reservoir are mainly formation damage because sand migration, right? The activity of the sand going from the inside the reservoir to my sand face is gonna plug my perforations and I can have a reduction of the permeability. So I'm gonna reduce my production capacity. Problems of the well could be many. Regardless the artificial lift system you are going to have, the sand is going to cause problems. You are going to have stuck lifting equipment. You may have wear in mobile parts, broken parts. If we are using rod pumps, we can have rod part. If we are using ESP, we can have broken shaft. We are using PCP, even with PCP, which is very good handling solid, we can have still problems. In the surface is where the problem could be more severe because the different connection, the use of control valves, instruments, separators, tanks, vessels, I could have many problems because of sand. I can lose the storage capacity of my tanks and I can have serious affectation in my surface facilities. How to control this? How can I manage this? And where can I set up my sand control system? So we can review this one in more detail. The sand control and management methods are different, are huge, and you can find different types. You can find sand control methods to use in the reservoir, in your artificial lift system, or at surface. One of the recommendations that I want to give you is use a sand control method at surface. Requires more equipment than use a sand control method downhole. Normally at surface, you have to use separators, accumulators, transport lines, and you can have a facility proper to dispose the sand, which means separate the sand from the liquid, then clean the sand, and then dispose the sand. So it is really complicated to try to control sand at surface, and it requires more equipment. Controlling the sand downhole is really proper. Using a sand control in the reservoir, it is one of the traditional methods, but it's at the initial can be effective. But with the time, we can have, like we mentioned before, sand migrating and clogging my perforations. So that's why we want to focus maybe on the sand control method. You can use maybe on your downhole equipment using a special metallurgy, which should be harder than the quartz, which is the typical normal component that form the sand. We can use production rate restriction, which means reduce the frequency of operation, try to control the PIV, the pumping the pressure, so in order to do not overcome too much the critical drawdown. Or we can have sand control methods below your pump, which means premium screens, you can have production screens, wire wraps, or you can have desanders. We are going to focus right now in desanders because it's the most worldwide technology right now, which is, and it is very effective. Like Gustavo said at the beginning, the cost-effective relationship is pretty interesting. And we want to focus not only how it works, we want to go beyond that and explain you how to optimize your desander. So this is really, Gustavo is gonna go deeper in this topic later, but I want to introduce a little bit. In order to set up a proper sand control method, you need to identify your problem, do a diagnostic, know what are you dealing with, right? So the particle size distribution is going to give you a highlight, it's going to give you an initial diagnostic of your problem. But you can't stop there. You need to go more deeper, and you need to consider that downhole, the condition that you have are different to the test or to the analysis you do that surface. Because at downhole, the sand can agglutinate and form a bigger and more complex mixture, which is really difficult to control. So it's initially I want you to think about it. Think about it, how different is the sand at surface and how different is at down. Okay, now we're going to go in the topic. We're going to talk about the desanders. First, I want to explain how a desander works and why we do all this analysis, why we did all these tests. We want to understand how a desander works. So, as you see in this schematic, normally production are becoming perforations, which are the orange arrows. So the production is going to flow until it reaches the intake, which is the slab at the top of the tool. The fluid, together with sand, is going to get into the tool. It's going to flow downward through the tool. It's going to have an inner pipe. We call that pipe deep tube. Sometimes you can find that they call it anchor. So that deep tube is connected at the bottom with the helix, which is the red curve over there. So that's the helix. That's the heart of the system. It is responsible for the radial forces onto the solids and then produce the separation. So when the fluid is flowing downward, it's going to reach the helix, it's going to flow through the veins, and is going to move radially or centrifugally, and then because the difference of density, the heavier phase, which is the solid, is going to go against the wall and is going to be separated by the radial forces. We can watch a video, but I want to first introduce you to our test facility. So looking for understand how this Desanders works, we set up a test facility. The test facility was made for 3 tanks, supply tank, another tank with sand and polymer mixture, and the storage tank which was connected to the production line. We used 3 pumps, one connected to each tank. The pump that we used for the sand and polymer mixture was a peristaltic pump, and the peristaltic pump was in charge of mix the sand with the polymer with the supply tank. The supply tank was mainly water. In this test as well, we analyzed viscosity effects. So what we did, we actually combined the water sometimes with glycerin with xanthan in order to increase the viscosity. Connected to the facility test, you can see right there how that's going to work. Can you play the video, Gustavo, please? So the video is going to show you how the mixture of sand with fluid is coming through the intake. In this case, we're using a screen as an intake. So the fluid is going through the screen and then is flowing through the veins of the helix. And if you see, all the mixture is going to flow radially. The radial forces are causing that the heavier phase, which are the solids, are being concentrated at the bottom. The lighter phase, which is the liquid, is going to be concentrated at the top close to the helix, because right there is where the suck point of the pump is going to suck all the fluid, the light fluid in this case. So we see how efficient, how dark is at the bottom, how clean is at the top. That's how a desander works in the real life, separating heavier and light particles. This is because differences of density. So now, the question that we are caring about right now is why and how optimize these sand control methods. Well, we need to optimize this because this contains separation efficiency. So that means the amount of sand we are going to separate with the desander, comparing the total sand production. Doing this, we can extend the run life of the equipment, right? Which means we can extend the production period, and then we have the possibility to increase the production rate, which means it's going to have we don't have to control our production rate. And economically, of course, doesn't help improve flow cash. Now the question is how to improve that. Well, Gustavo, please help us with these questions.
Thank you, Luis, for all the presentation that you did in how the Desander work and kind of the background of the entire system when we frack the well and how the production is actually affecting some of those parameters. One of the things that we can see on the operation efficiency is more we need to be aware about what kind of helix are we planning to use. What I mean with this is there is more than 60 different sizes and different angles that is going to be related with the production of the throwdown that is generated with the pump or alloys that they can help you with that operation. The type of intake, traditional desander is normally slotted or perforated. So we can actually use screens to be able to generate a previous filtration point prior to the desander. So in that case, we can increase the efficiency. Another important factor on the fluid properties, we can see the viscosity and the density contrast. We're going to see some tests and some calculations based on that, how the viscosity can affect the filtration and the efficiency of my desander or my in my heated pores, what you describe as the radial forces and also the linear acceleration that the particles are taking when it pass through the veins. The production parameters, how we say the pumping speed or the frequency based on the type of artificial lift system that we're dealing with, and the fluid rate, how much fluid is passing actually through the system. Another thing that is important, more in unconventional wells, as you described at the beginning, we see different peaks. We see production that is start maybe at 4,000, getting a peak, maybe I get my child well that is affecting, and now my parent well, due to the pressure, is sending some of the fluid to my shower well, and I see a peak, and now my well is lifting 7,000 barrels per day, and is declining in less than a month to 3,000. So all those deplete particle size distribution. What we mean with this is based on the type of frac sand that we use to frac the well. So normally is around 100 mesh for around 50% and some 40-70. We use a combination of that. That can affect also more deformation sand that is coming or is migrating to the system. That is going to create a little bit of difference on the particle size. So on the operational efficiency, as we described at the beginning, we're going to talk about that helix, those angles, the veins, and the jetting area that we're creating. We apologize for the inconvenience. I think we're having some issues with the connection. Our IT department is working on it because we're not seeing the full view of the screen. Give us a minute, please. So I think we're back online. Like I said at the beginning, we really apologize for the issue. I don't know how far you guys were able to hear, but one of the things that we were saying on this slide was more the relationship or the correlation that we have with the design of the helix and the jetting area, that is the one that is creating that centrifugal force, and it allows us to generate the linear acceleration for the particles, so the particles can fall down to the mud joints or tailpipe, and the fluid can return inside the helix. In this case, we see the correlation based also on the microns or the particle size distribution, how big is the grain, and the different type of angles that we have on the helix. One of the most common things that we can see based on this artificial lift system that we're dealing with, in this case, is an ESP. So the main thing that we see on ESP, we get a bigger angles. The veins are going to be wider. One of the main reason of that is because we have a lot of fluid passing through, and we need to be in consideration the depletion curve that we're planning to use for each particular well. In this case, we're giving you two examples. It's a well that is producing around 500 barrels per day and is depleting to about 350. In that case, based on the type of particles or the sizes of the particles, is going to be a different efficiency. And that have a relationship based on the drawdown that I'm generating with my pump. So we can see if we're dealing with most of the 100 mesh, we're going to see 100 micron, we're going to see if we keep a fluid production, we're going to see a high centrifugal force, and the efficiency is going to be close to 85 to 90%. But one of the things that we need to have in mind, that ESP is not producing the 400 barrels per day constantly. So our efficiency is always fluctuating based on 80% to 90%, because we're always getting a little bit of changes on the flow rate that is going to be related to the drawdown generating to the system. And what it means is when the fluid is passing through the veins of the helix, we can see in this photo, the linear acceleration that I'm generating of the particles is going to be different every single time. So that's why it's so critical. Use the optimal range for each system based on the production. On this second case, we can see on the helix that is what we call like 2.4 is for higher production, and is more for wells that is keeping a range between 600 to 800 to 405 barrels per day. It doesn't mean that the desander or the vortex is not going to work if we have lower production. What it means is every time that I am a little outside those ranges, my efficiency is coming down. It's going to be created below the system. So in that case, we can see is a little more fluctuation on the vortex by themselves, because one of the things that you're going to see is normally is my centrifugal force was generated in this chamber that is designed specific to control this chamber that we see over here. Is designed specifically to control that abrasion, that high centrifugal force. Is we're undersizing the helix and we're operating with a higher flow rate. Now the linear acceleration generated in the system is going to force that centrifugal force to start in this point. So my drawdown is bigger, and what I'm going to do is cause that abrasion into the tailpipe. If that system is operating for just a couple of days, it's not going to cause any damage. But what we need to have in mind is every single time that the sand is passing through the wall of the system, it's going to start to deteriorating some of the material. That's why the chamber or the housing where the helix is located is a high resistant abrasion system to be able to handle that volume and that centrifugal force. Let me clean this out and we go to the next one. If I'm dealing with a rod pump, I'm going to see the same phenomenon. In this case, the drawdown is going to be alternating based on the upstroke, and so the helix that I was using before is going to have a different ranges for my rod pump. And one of the things that we care operator is when we're doing that transition and switching from ESP to rod pump, there is always an opportunity that we can bring those equipment back and readdress whatever is needed. Most of the case is just the helix, the one that need to be changed or resized based on the target that now we're planning to have in this particular case. Normally, for trying to make this a little more simple, we try to give you like a flow chart. In this flow chart, we show some of the ranges, so it's a little more easier for you guys to choose which helix is going to fit the most, or is going to be the better fit for each application based on the total production or the ranges that you get in the system. And also we get different sizes based on the tubing size, so that helix is going to create some changes, but the bands or the space or the open area that you're getting around those bands that we get on the helix is going to be the same. Talking about the length of the tool and the sleeve, this is going to show a little more details about that centrifugal force that we discussed at the beginning. So when the fluid go through the slotted portion of the intake and now falls back due to the drawdown generated in the system, it's going to pass through these veins. When the fluid is passing through the veins, we're going to see an acceleration in this section. So I'm going to make some drafting over here. So when the fluid is coming down and is passing through the veins, it's going to cause that centrifugal force, and the particles is going to have that to see different type of damage, or what we call kind of the wave generated by the vortex. We're going to see that it's going to start to affect in the system. We always want that centrifugal force to be generated in this chamber, as we discussed in the beginning, but the drawdown generated is we're dealing with a rod pump. Either the changes on the amount of the sand that I am producing through my system, or the changes between the stroke length or the pumping speed is going to cause a different drawdown in the system, moving that wave or moving that starting point from the centrifugal force a couple of inches. So in this case, we can see a radial force for the vortex that is starting almost 0.5 to 5.5 inches from this point. And in this case, due to the high sand rate that was passing through and the high volume of fluid, now we see the affectation point or the damage being generated around 13 inches to 15 inches. We're going to show you some photos of some of the desanders that our customer has been asking us to check to evaluate what maybe was the cause of the damage or what was the reason of the pull. That's something that we do as part of the service. And this is some of the formulas also that we use based on the metallurgy that we're applying in the system. Either if you're using an L80 or a J55 or a high abrasive resistant equipment, we're going to see that when the sand is passing through and is creating the centrifugal force around the veins of the system, we normally have the helix located around this point. This is where normally the helix. And if I have in mind this is going to be the wall of my system, the particle, when it's passing through the vein, is going to start to erode and eat some of the metal. And it's going to start to decreasing that or eating some of the material that I get on my sleeve, on my mandrel, and it's going to start to increasing that ID. So this is what you're going to see based on the type of desander that you get on the market. We normally are evaluating the penetration rate that we get through the system. So in this case, you can see that the helix was landing over this point and the penetration rate was low. All the sleeve was in good portion. You normally see a lot of sand when we're pulling the system, but we didn't damage the mandrel in a high severe case. If you see like this other photo, we maybe see a little more corrosion that there was attacking the system, but at the same time, we see some damage or some marks through the system when the fluid was passing through. Also, we saw a cut over this portion due to the centrifugal force. You can see in this one, we still have the helix over here, so you can see a little more clearly the marks that was generating that centrifugal force. And this one is more like a high penetration rate. We see severe corrosion issues, but at the same time, we saw a lot of high volume of sand passing through the vortex, and the size of the helix was not the appropriate based on the ranges that this well was producing. So most of the case, either it got affected by an offset frag, so increase the total fluid from the system, and the helix was not able to handle that ranges for a longer period, and that's why we're going to see some of the severe marks through the system, and we see more damage until the point that the majority of the operators that are facing is either they start cutting that tailpipe or cutting the desander. That's why it's so critical to size everything appropriate, and that's what is the main topic over here. Desanders, how we mentioned at the beginning, is one of the most common due to price, due to the simplicity, but at the same time, there is a science behind how to choose the right helix based on the flow rate that you're handling and the type of particles that you're producing. In these other photos, we're going to see more severe cases where we actually cut that thread connection. In this case, the internal portion of the sleeve, we see everything in a good shape. There was no damage. There was no damage through the system, so the sleeve didn't have a severe mark just at the end. But one of the things that we see is the tailpipe that was underneath it, or the mud joint where the sand was stored, it started creating too much centrifugal force that we see at the end of the connection of the collar. We actually cut that tailpipe, and it was because the drawdown generated through the system, it was higher, that it was pushing that centrifugal force around 2.5 feet, and that's why we start to creating the damage in the tailpipe. And as we mentioned before, we always want that centrifugal force being generated in the sleeve. This other photo, it shows in a well that was producing around 350 barrels per day. We got a runtime almost for 2.5 years, so it was a rod pump. But one of the things that you can see, because there was two different ranges on the production of the well, when they did that conversion from ESP to rod pump, they got a higher rate that was passing through the Desanders. So we normally see around 400, 450 barrels per day. So that's why we see the first mark. So the higher drawdown and the fluid that was passing was pushing that wave a little further. After the well was depleted, after the first year, now that cutting out inside the sleeve, it was moving a couple of inches, getting more close to the helix. That is a normal phenomenon that you're going to see in any desander. A desander is designed to create that centrifugal force and start to eat some portion of the steel if you're achieving a high run life. In cases like this, that's a good opportunity where we can decide, change the metallurgy of the mandrel or the sleeve to be able to handle more abrasion. So that's why we got different materials. Carbon steel is one of the most common, but it have low corrosion resistance and low erosion rate. The majority of the parts that are built with that is either the deep tube, the intake, the sleeve, and the helix. One of the changes that is normally recommended to do, if you have a high corrosion environment, maybe go with a stainless steel, but the stainless steel is going to be soft material, so if you have a high volume of sand, you can protect the system now for corrosion, but it's not going to help you with erosion. So if you want to keep that balance and get something that it can help you with high corrosion environments and high erosion rate, we suggest to go with a special alloy that we provide. That special alloy is going to be actually around 75% harder or 75 times harder than a traditional carbon steel, and it's going to help you to handle more volume of sand without cutting the desander or being affected now with some of the issues that is going to cause either a fishing job, and now it's going your pooling is going to be a higher cost. It's going to oscillate around 400,000. So for cases like that, we give you multiple options, but always have in consideration that portion. Another thing that we're used to, just like traditional desander, on the test that Luis was mentioned at the beginning, one of the most important things that we saw was every single time that you're changing that intake portion of the desander, of the vortex desander, we're going to see an improvement. So traditional desanders is going to be just perforated or slotted, and we see a lower efficiency when we're dealing with a 100 mesh. And in the Permian Basin, that's kind of the most common micron size or particle size distribution in some of the wells. But when we have the combination with the screens and the vortex desander, so now the screen becomes the intake, and what the screen is going to do is break that agglutination, that chunk of sand when it's passing through the screen, you're breaking that out and being able to create a better acceleration or a linear acceleration for the particle, pushing those particles into the tailpipe. That's why you can see a better or a higher efficiency with a lower micron size. And every time that the micron size are increasing, the screen is going to handle more of that sand or a bigger portion of that, and the remainder is going to be with the vortex. So on the properties, we're going to see that the viscosity of the fluid is going to play also an important play in this. Every time that we're changing that viscosity, those centipoises is if we're dealing with one centipoise that is kind of the most common in the Permian or the New Mexico area, the sand still be able to break or separate from the oil. But if we're dealing with maybe 20, 50, 60 centipoises, we're going to see a little more viscous fluid. It's a little more jelly, and it's able to trap some of the smaller size of the sand. So the sand is going to be trapped with the oil, and it's going to be more difficult to generate that centrifugal force to separate those particles. So the bigger chunks are easier because either you use a perforated joint or a screen to be able to push those out from the system. But the finer sand is going to be trapped with the oil going straight to your pump. So that's why we do also the relationship between the density and the contrast that you're going to see. Have you guys watched on the test when we were dumping the sand and we were pumping the fluid, we normally see that the sand particles was creating that linear acceleration, pushing all the sand into the tailpipes and allow the fluid to return inside the deep tube. So we normally see this more based on the gravity and all the forces that is generating through the system. Our point with the viscosity was every time that I'm changing that centipoises or that viscosity from the liquid that I'm lifting is going to be able to trap more sand and start to decreasing my efficiency based on the helix or the ranges that I'm using. In this case, we're going to see those pumping parameters or that speed that we have in the system, is it an operating on an ESP or a rod pump. This is a good correlation that we saw before. So the speed is going to give me an efficiency point. Well, how we calculate that? That is when the fluid is passing through the intake point that you're facing. Either if the slotted portion or the screen is calculated based on the fluid that is traveling between the OD of the inner tube and the ID of the tubing that you're using, that fluid is going to have a linear acceleration velocity in that point, and based on that and the veins that I have at the bottom of the helix is going to give me an efficiency. Normally on ESP I get more constantly fluid passing through the pump, so in this case is more like a graph based on ESP, so you can see that the optimal ranges is going to be to achieve an 85% efficiency is going to be around 26, 27 inches per second. Once I'm achieving that fluid velocity in that point before it goes through the veins of the helix, my efficiency is going to be higher. As soon as the well is depleted, my efficiency starts coming down a little bit. And another thing that we have is that the pumping speed is normally directly related to the separation efficiency. Why? Because the drawdown that I'm generating with my pump is going to be pulling the fluid harder, and that mixture that is between fluid and sand is going to cause that acceleration. At the same way, we did evaluation between the production rate or the amount of fluid passing through, is we're oversizing the helix. So if you get a bigger veins in the same production range, you're going to see that your efficiency is increasing. In this case, it's more like this is the efficiency curve that I have in case I am using a 2.4 helix. If by mistake my supplier gave me a helix size that was bigger than that, now like a 2.8, 2.9, now my efficiency for trying to handle 250 barrels per day is going to be low. You see the big change between 68% is coming down to 18. And it's more because now when the fluid is passing through the veins, I'm not creating enough centrifugal force and I'm not forcing those particles to have that linear acceleration. So the particles are not falling into the tailpipe and it's just returning inside the inner tube. And once again, one of the things that we're showing this photo again is because we want you guys to visualize this is the sand that we normally are dealing with. Every time that you guys go to a tear down, either for a rock pond or an ESP, check the sand that is accumulated into the tailpipe. Get a sample from the sand that is inclusive in your pump, or get the opportunity to get some sample from if you have any sand leaf or any device that is helping you to capture some of the sand when you get those chip downs on ESP, get the opportunity to evaluate the particle size distribution and how that sand looks like. So this is the sand, how it always looks like when it's mixing with the oil. And if the viscosity is higher, that chunk or that agglutination is going to be more difficult to break. This is the sand, or this is the same sample that we get. And in this case, we're removing the oil. What we did was almost drying all that oil, cleaning that sample, but now you see particle by particle. In this case, is I use a combination with the two stages filtration, how we call it, that is what we mentioned before, having the opportunity to have the screen as an intake and not just a slotted stuff. We're going to see a higher efficiency because I am delaying that time for all this sand or the chunk of sand to go inside the system. I am giving more opportunities to increase the fluid velocity internally and allow the helix to handle better the particles when are passing through the veins. And this is part of the test. We're going to see that based on that particle size distribution, in this case, it's more when the sample is dried and is already removing the oil and water. So we see more the weight of the sample. So we see some 1200 microns, 381, but a higher percentage was more 305 microns. So in this case, we did the correlation between just two factors. Forget about, for this point, forget about the total fluid passing through the system. In this case, was more having an idea. So the two factors that we're evaluating is just the microns, the particle size distribution, that it is, and the efficiency that it had. In this case, the only external variable that I'm adding is more the viscosity. So every single time that I'm increasing my centipoises or the viscosity is higher, my efficiency for minor or finer particles, that is this portion, is going to be lower. And every single time that my viscosity is low, my efficiency on the finer particles is going to be higher. That's what we try to show with this portion. So if we're dealing with 300 microns, I can get for this particular sample and this particular helix, I can get around 50% efficiency just with the helix by themselves, and I can knock out already like 60% of the sample that I have from the system. The angle of the helix. So now we did the correlation between the same particle size distribution, or PSD, based just on the angle from the helix. And we see that regardless that we change that angle or that inclination between 1 to 10 degrees, we're going to see around the same centrifugal force through the system, because everything is more related with the drawdown that I'm generating, or how hard that I am pulling that fluid, and based with those differential pressure that I have on my system, that's what is going to create that centrifugal force. So the angle was not a major factor for this particular case and this particular sample that we were evaluating. So one of the things that we can conclude, if I have a particle size distribution, something that is showing like this. In this case, that sample was collected from the tailpipe or the mud joints. So after I put my 2 stages filtration, we see that the sand that was now stored in the tailpipe after I pulled my well, it was now changing. The reason of that is because those particles were controlled by the screen, but why the finer particles now is lower than it was before. And the reason of that is because that screen is creating a coalescent effect. So every single time that the fluid is passing through the screen, I am baffling that sample or that sand or that chunk that is coming from my well, and I am suspending those solids around the system, around the screen. That sand, because it's so lighter, it's not falling down through the bottom of the well. What it's just doing is just stationary, passing through until the point that the sand becomes smaller and now goes inside the system. But why this portion also decreased that much is because now what I did is allowing my pump to deal with a small portion. Before that, I was allowing everything to be stored into the tailpipe. Now I am giving almost like 3 stages. The first stage is with the screen, the second stage is with the vortex or the desander, and the third stage is allowing my pump to deal with a small portion, around 5 or 6% of the sand that is passing through the desander. So in that case, I'm not filling the tailpipe fast, and I'm giving more time to the system. Some of the operators were asking about, if I have a desander, I don't want to deal with 100% of the sand, or I don't want to deal with any sand. Remember, we cannot disappear the sand. Either we're pushing that sand outside the system, outside the desander and the screen, or we're allowed that sand to be stored 100% of the tailpipe, or allow the system to start producing a small portion of the sand. Every time that we're designing a rod pump, we're calculating that clearance or that fit between the plunger and the bottom. A rod pump is designing to deal with a small portion of the sand. The problem becomes, and the reason that we get some wear plunger, is because we're allowing all the sand to go through at the same time. That's the issue. In this case, we got a high runtime, and regardless that we shift this, we didn't see any severe marks around my plunger, and I was more giving the opportunity to my pump to deal with these finer particles. And this is kind of this combination or an schematic of what we discussed before, using in this case a 12 slot that is almost equal to 308 microns. We were able to separate a good portion of the sand, and we were able to change the particle size distribution. In this case, one of the things that we did is just playing with the velocities internally. So when the fluid passed through the screen, and the linear velocity inside, when it was passing through the veins of the helix, was creating a previous acceleration to increase that centrifugal force and create a better filtration. So that's one of the reasons that this type of configuration is getting a little more popular, is more for the benefit that we get through the system, creating those 2 stages. And now we got also some of the case studies that Luis is going to talk about.
Okay, thanks, Gustavo. This is a small picture of what we have done, we have made through the optimization of the Desander. So if you look at in the graphic, we have orange and then green bars. Orange bar means wells using Desander, and then the green bar means wells, the same well using Desander, but optimized. with all the criteria Gustavo explained before. We talk about hillet size, we talk about angles, jetting area, we talk about type of intake, we talk about fluid properties, and we talk about the distribution of the particles, right? Many of these will have problems because either they had a wrong hillets, I mean the production that they were getting was so high or so low, and then they were having problems. When the production was so high, they had sand cutting problems. And when they pull the well, they have fishing job, right? So that's a big deal, and it is really expensive. And other cases where they were producing low volume, so the hillets was oversized, as Gustavo explained before. When this happened, the separation efficiency dropped down drastically, and the sand was going through the hillets and then reaching the pump. When this happened, they have to pull the well because they were having some problems, erosion, the pump gets stuck, or they have abrasion on the sleeve, etc. So what we did was we take the data, we did the analysis, and we designed the proper desander for each tool. Some cases they needed to have a longer sleeve. In other cases, they have to use a different material in order to be resistant to the abrasion of the solid. In another case, they have to combine a different intake. And the other one, the most common one, was wrong hillet size. So we changed all these parameters, all these factors that were making ineffective and reaching and was achieving a poor performance. We changed that and we installed a new desander. The results are here. So it is really evidence that not because you are using a standard tool that was proved effective in one well, it necessarily has to be effective in my well. We proved that doing the right changes to your specific condition, maybe not only from your well, but maybe the specific condition of your field, you are being able to reach maybe double or triple the runtime you were achieving before using a standard tool. If you see, for example, in the well 7AA, the runtime was around 68 days. After installing a new desander with a new optimization, we were able to reach, and right now it's running, more than 260 days. So sometimes, like Gustavo and I explained before, the well is going to be hit by an offset well or a child well. And if you don't have the accurate metallurgy, if the amount of or the hillets that you are using right now is not the proper one, you are going to have really difficult problems dealing with sand. And then the message here is plan your sand control system, optimize the components you need to optimize, and I'm pretty sure you will achieve the runtime or the production you are expecting from your wells. This is just a small picture of what you can achieve optimizing your sand control device, specifically your sand. Okay, we're right now in the conclusion. So, like I said before, using a standard tool and existing technology is not always a guarantee that your application is going to be successful. The recommendation is design the parameters, analyze your condition, and adapt or maybe fit, match this new technology to the conditions of your field.
One of the other things that we can see from conclusion is like based on the pumping speed or based on the hertz on the frequency that I operate in my system. One of the most influenced parameter for better sand separation system, it was more that drawdown generated, and also the inappropriate design could cause a reduction between 40 to 70% on the sand separation.
Okay, another really relevant conclusion that we can get from this analysis is hillet size, jetting area, tool length, and the materials are the most relevant parameters to optimize the design of the vortex desander. If you consider these parameters in your design, you can have a really, really reliable tool downhole.
The type of intake that you're implementing, as we mentioned, based on the test that was done, is going to play an important role. If you're using two stages filtration versus just one stage, just imagine, like Luis mentioned at the beginning of the presentation, how much sand do we actually use to frack our wells? More as a new well, that when I don't have enough bottom pressure and I need to put my ESP to start to dealing with the majority of that frac sand. So I can feel my tailpipe super fast, but having the two stages is going to give you a better handling method to start to lifting the particles and being able to cause less abrasion and erosion damage on the sleeve by themselves. So be sure the screen is not for all the wells. Like we said, we cannot copy and paste and put exactly the same tool in every single well. There is going to be some resign and some adjustments based on the condition per well or per field. But the intake is going to be an important factor to be sure you are achieving the efficiency that you're looking for.
Regarding the fluid properties, the viscosity and the density contrast were very important. However, it is really difficult to control these properties. Unless you are using maybe a thermal recovery method. But even if you can control this variable, it's really important for you to be aware how these variables are impacting the performance of your technology. What I mean is, not all the technologies are applicable for all the wells or for all the fields. You need to do criteria analysis, you need to choose the right tool. And for example, if you are reducing heavy oil, you are not reducing your viscosity, I mean, you are just producing high viscosity fluid. This kind of technology will not really help you with sand control, and you may need to look at a different method like homogenization and then try to maybe produce the sand instead of just
we can get as a conclusion was like the angle of the helix was not a significant impact on the results, and the main point to analyze is the helix design for the production rate. So we know several operators have asked on the past, what about if I modify the inclination of the vane instead of being like 45 moving to 38 or 37? On the test, we saw that it was not a major change on the performance, but the production rate and the drawdown generated in the system, it was most critical, and it was the decision factor to increase or generate a better efficiency through the entire system.
And then finally, the particle size distribution will rule majorly or is going to affect highly the efficiency of the separation. As Gustavo explained in his presentation, the relation between the particle size distribution and the efficiency of the separation has a direct relation with the separation efficiency. So it is really good to have always in mind that if we have a specific sand distribution, we have to not only keep in mind factors as the helix, but we need to keep in mind the type of intake. And then if we have another maybe well which is coming soon and it's going to affect the performance of my tool because they change or the resorting of my distribution. So all the type of sand could be controlled if we come out with the most accurate design for your sand control system.
Thank you for your time, and we're going to answer some of the questions that have been generated either through the YouTube channel and through the Zoom webinar. One of the questions is, what is the number of the mod joint that you will recommend to run below a Desander that is installed on an ESP? So there is not a magic number. I know longer is going to create a better runtime because you can store more sand, but you need to have in consideration is the amount of weight that you're putting below the ESP. So when you do the number, not just having consideration an inky tubing, but having consideration the total weight with sand. And normally, what we see in the Permian Basin, we try to go between 8 to 10 joint max. And the majority of the cases in Rock Home, they go between 7 to 9 mud joints, and that will be based on the severity of the problem that you're facing. Another thing, please have in consideration when you are analyzing to run any desander, or if you want to add more tailpipe, please calculate the doublet and the inclination, just not at the sensor or the bottom of the ESP, but also at the bottom of the tailpipe, because you don't want to have your ESP almost at 1 degree or 2 degrees at the bottom of the tailpipe because you decide to use 12 tailpipe joints, and now the inclination is going to be about 40 degrees and the doublet is going to be higher than 70, because now what you're doing is actually pulling the shaft to one of the sides, and you're going to generate more issues on the future.
Well, another question is that if can we design a desander that can help us with considering the frac hip? Okay, that's very common. That's a very common problem when you are operating a well, and then you are having a frac well and an offset well coming, and then it's affecting your performance. Like we said at the beginning, there are different things you can do. Talking specifically, you have to design your desander with high resisting material, which means your vortices slip have to be able to withstand the overproduction, the high production coming. That's one of the things that we need to analyze. The material of your desander. Secondly, you need to be aware about the production you are expecting. I mean, if you are producing X value and you are expecting a Y increasing, you need to get a proper helix. However, it is really difficult to pull the wheel just to change the helix, right? So that's why I'm telling you, keep in mind the material is gonna affect highly the longevity of your well downhole. That's one of the things. The second thing will be more operative measures. So while you are fracking this well, you need to shoot this well down. So the impact is not going to be direct. And you can control at the beginning of the production of this well the velocity. So you are going to start producing to low velocity, low pumping speed, and then try to drag as less sand as possible. And you create a sanding communication between the wells. When you do this, you can control the amount of sand you are producing at the beginning. Then after 1 or 2 months, maybe 1 month of this type of measure, you can start producing normally, considering that you have a high resistant material that is standing the erosion producing for the high production rate of sand.
Another question that we have is, can one helix fit all the production ranges? I think, as we discussed in the webinar, one helix cannot fit all the ranges because due to the centrifugal force that is generated around, plus the linear acceleration for the particles. And I will answer more like, can one of your ESPs be able to produce either in 5,000 barrels per day or 350? No, it can't. And the reason of that is because all your ranges that you have already for the motors or the stages from your system is going to generate a lower efficiency if you're depleting the well like that. So it's almost the same thing. We're based on the drawdown generated at the bottom of the helix. That's why we always need to adjust this based on the total range and the target that you have per well. Normally, I will recommend, if you get a new well and you don't have any clue about what is going to be the total production or the target, you normally have an estimated number. Your planning may be to produce 4,000 barrels per day initially, and in less than 4 months, you're needing to 2,500. One of the things that I can do or we can do for you will be size that helix for kind of a middle point. You're going to face a little more acceleration at the beginning, but at the end, you're going to keep everything at the depletion curve for that year. You're going to keep almost in around 85% efficiency for the separation of the desander.
Here's another one. Why it is so important, the length of the tool? Well, I think we detailed this very much, and the reason is because the radial force you are experiencing after your helix is going to displace down in your tool, right? So normally the sleeve that we use to catch this radial force is a double wall sleeve, which means it has a good protection in case you have sand erosion. The problem is, as you increase the drawdown, the displacement of the wave is going to increase. So the effect of the radial force in your tool is going to displace downhole, right? So if your sleeve or distance between your helix and the bottom of the double wall is short, this displacement is going to move inside the mud joints. I think Gustavo showed some pictures where the mud joint was cut because the sand. So that's what we want to avoid. We want to avoid that the centrifugal force is too much to reach the mud joints, which has just one wall, and then catch the whole centrifugal force or radial force inside this double wall sleeve. In that case, we're gonna avoid sand cutting, and we will extend the run life of the well.
Another question that we have was like, we have designed many wells with 100 mesh, leading to the frag is 4070. A desander will be enough to handle the frag sand. We're completing this with ESP. So normally a desander can handle some of these problems. Again, that will be based on the information that you're actually producing and some of the historic of that field. But yes, the answer is a desander can help you with that. If there is a new well, I would recommend to go with a better alloy to be able to be more resistant with erosion and abrasion, because normally if there is a new well like you're competing with ESP, you're going to see a little more changes on the ranges. Like we mentioned before, from either 5,000 you're coming back to 3,000, and the changes are so drastically that you can generate too much centrifugal force and cut the desander. If you're concerned and you normally see a lot of tailpipe that you're feeling in some of the other wells, I will recommend to use the two-stage filtration. We have a great success on the Permian Basin and Delaware Basin using this type of equipment. The benefit that we see with the operator, we don't have the damage on the ESPs or the stages, and we avoid the slugging issues when we're slugging, not just with gas, but when we're slugging with a lot of sand. Most of the cases for maybe Howard County, Midland County, when we don't have enough bottom hole pressure, and we're putting the ESP after fracking the well, and we have all the frac sand that is suspended with the fluid, and the pump is going to leave everything to the surface. So that's where you see the majority of the benefit. If you have a well that they have enough bottom hole pressure, and you have maybe a flow back for like 5 months or 4 months, you already clean around 30 to 50% of the sand that you have in the well. So you are not going to face severe damage on your ESP. That's why maybe I will decide to go just with a regular desander, and I don't need to add that additional price on changing the metallurgy of the system. I don't think that we have any more questions so far. Luis, do you have any other one?
No, that's it. I don't have any other question.
So that's it, guys. Thank you for your time. I hope you guys really enjoy it. Thank you for watching us. We try to come every week with a new type of webinar. If you guys have any specific topic that you would like us to discuss, please send us an email. Let us know. Also, we can do like private webinars with you guys and your team, so we can evaluate and we can study either a particular path that you guys are planning to frag or planning to complete with ESPs, or maybe older wells that you have in Cloud Pond that is not giving you the runtime that you guys are looking for. Right now, as you guys know, the oil price is not really that high. We all are facing these economy issues. So that's why we need to optimize. We need to find new alternatives, new solutions. We need to think outside the box to be sure why we can do or how we can invest in something that they can help us to decrease the operational costs. So that's why we're over here to help you. Thank you for your time and have a wonderful day.
Thank you very much.
Bye.